Okay, I think we are online now. Yeah,
Okay.
Sugam, shall we start today's session then?
Yes. Thank you.
Okay, okay then. Yeah, good evening to all. So let's start today's session.
So as usual, I think I can just switch off my video just to make sure that nothing overloads. Okay, so you can see my screen.
Yes, sir.
Okay, perfect. So
Yes.
in the last class, we discussed about the quantum gates. And today, little bit, I will extend it before I go to the quantum algorithms. So,
Sir, one question I have to ask.
yes, please.
That is, you taught C naught yesterday, C
Yes.
naught yesterday, and
Mhm.
there one thing is my query. That
Mhm.
is how the matrix formulation of the C naught can be deduced. You gave there has been a forecast for matrix. How to deduce the matrix out of the result? That is my problem.
But I think I wrote matrix notation now, right?
Yes,
Matrix of
yes, you
this.
wrote it, but how does it come actually? That I didn't understand.
So see, these all Pauli matrices, okay, they are, look at their operator, correct?
Okay,
And generally, if you look at the operators, then these operators are written out of their functions. Okay, let me give you one example. Then I think it will be not only for C naught, but it will be general for every operators. Okay.
okay.
So, for example, we are, let us say, working in a 2-dimension. And I can just show some grid lines. So this is 2-dimensional space. I'm just taking a vector space, okay? Normal vector space, a 2D vector space. And
Okay.
in this vector space, let us say that I have these are the two our basis vectors, which I can call as the I, and this I can call as the J.
Yes.
And now imagine that you want to rotate this space.
Hmm.
And you want to rotate this space. What happened? Just a minute. Okay. So so you want to rotate this space, and this I and j as given. So definitely you can see that this vector will be here, let us say. And you rotate by angle 45 degrees, so that this vector goes in this direction and this vector go to this direction.
Yes.
So definitely you can see this is the rotation you are doing. Okay. And let us say now this I cap go on here and j cap is here.
Yes.
So now this whole mathematics or the physical task you are doing, what is the physical task here? That you rotating the space in anti-clockwise direction by angle theta.
Angle theta.
Okay. So this transformation,
Hmm.
I can represent by a matrix, and this is 2D case. So definitely this whole transformation, which I can call as a rotation transformation, this is going to be 2 cross 2 matrix.
Yes, yes.
So you can see that I know what I'm doing, and I have to represent this in the matrix form. So that why we do this, for example, let us say if I have any vector, okay. So think about that my vector is this, that is called r cap, r vector.
Yes.
And after the rotation, when you're going to rotate the whole space by theta degree, then where this r will go? Okay, either you can look it physically, or maybe if you know this matrix, okay, then what I can do simply, I can just operate this R. Let us say this is the R matrix. So this R you can operate on the R state, and you will get the Q state, okay, directly without looking at the geometry. If you know the
Yes, yes,
matrix,
it's a
so
gate. It's
it
acts
is
as a gate.
act like a gate, and this is what C naught is also. So all the gates can be written in this format. Let us say, let us write down this R, then you'll understand. So for example, if you look at I, so I is nothing but a 1 0,
1 0
and J is nothing but a 0 1.
0 1.
Okay, but if you look at the I dash, okay, so I dash is what? It is actually
There
a
there
1
is
1,
a
correct?
e to
I'm
the
right?
power I theta.
No, this is 1 1, correct? No, if you look at the, so this is one unit in the X and 1 unit in the Y, correct?
Yes, yes,
And look at the J. So J is nothing but a -1 and 1, correct? Sorry, plus
yes,
1 and -1. X is in the minus direction.
yes, yes.
And now I can tell you that this new operator R, very simple. No, I mean, you can write it also, but this is going to be a technically a new I and new J. So new I means what is new I? 1 1. And what is J? 1 minus 1. And you can see that this is the operator 1 1 1 minus 1. This is representing a rotation operator. Rotation operator
Mm,
rotating space anti-clockwise.
mm,
Okay, and this is by 45-degree, correct? No, you can see that we specifically chose 45 so that key this goes to this direction. And now you see what happened if you apply this R on the R state. And this R is what? Look at here. This R in the vector term written like a what? A 2 time I cap plus 1 time J, correct? Nothing but
mm,
a 2 1. And look at here, this 1 1 1 minus 1, and this is going to be a 2 1. This is going to become what? This is going to become 2 3 and 2 minus 1 1. Okay, so
1.
it means that this vector after the rotation, okay, this vector will go to 3. Did I do some mistake?
One entry is 3. That is right. And another entry that is also 1. No problem, I can see.
There's a problem in writing the matrix. Okay, so this J will be equal to actually a -1 and 1, correct? Yes. So there is a problem. Okay. And this is going to be a -1 and 1, -1 and 1. So here, this is the matrix issue. Okay. So this is 1 minus 1, 1, 1, and this is going to be 2, 1. So this become then 1 and 2, 1,
0.
and this is going to be 3, correct?
Yes.
Now it is correct. So you can see that even I have to extend this one a bit step further. Okay, and you can see that this vector will be gone to here. I'm right. That is the Q vector.
Mm.
So even without looking at the geometry, you know that key where the vector will go now. So this is how I can write down this matrix. So this is also gate. Okay, this is the way all the gates, mathematics or matrix you can write down. So
Okay, I will try this for C naught.
exactly, you can try for all. Okay, not only for C naught, but even for X gate, Y
Swap,
gate, Z
swap,
gate. For all
swapping.
the gates, yes, exactly, all the gates. This mathematics, just to look at key, what was the I, what is the new I, and what is the new J. Okay, that become the new matrix. In 3 dimension, it is going to be a I, J, and K also. But here we
Yes.
are dealing only with the 2 dimension. That's fine.
Yes.
It will work.
Yes.
Okay, good. Just try out yourself.
Okay,
Otherwise,
okay. Thank you. Thank
it
you.
it is good mathematics to do. So we discuss about all possible gates in the last class. Maybe I can just give you summary so that of all the gates so that it become just easy for you to understand. So we discuss about single qubit gates. And in this, we discuss about the poly X gate. And symbol is this one, X, and like this. This is how we use it. And in the matrix, this is nothing but a 0, 1, 1, 0. And what it does, when you're going to operate X on 0, this is going to make it 1. And when this X operate on the 1, this is going to make it 0.
I cannot get.
Then second is the poly Y gate. This is what we discussed yesterday also. So the poly Y gate by symbol we represent by this. This is just a sigma or poly matrices. So 0 minus iota and 0. And what it does, so when the Y operates on the 0, it
I
I
iota
1, correct? And when Y operate on the 1, this is going to make minus
minus
I
iota 0.
0. Then third is the poly Z gate, and we represent by this symbol. And this is the sigma Z matrix 1, 0, 0, minus 1. And you can see that given this Z operate on the 0, it does nothing, no?
Doesn't change.
But when Z operate on the 1, this is going to simply make it
iota
exactly minus 1. E power pi, iota pi, correct? Then we discuss about the Hadamard gate. So Hadamard gate symbol, we use H. And in the matrix form, it is a 1 by root 2, 1, 1, 1, minus 1. And what it does, so when this H operate on the 0, it is going to create a superposition state.
superposition.
Exactly. So this is going to be 1 by root 2.
0
and
plus 1.
Plus 1. Very good. And when this H operates on the 1, this is going to become 1 by root 2.
0 minus
0 minus 1. Then the fifth one also I did not talk about yesterday, but something called phase gates. So in the phase gates, the one gate is called S gate. So one is called S gate.
Yes.
And the matrix is 1, 0, 0, iota.
Iota.
And when this S operates on 0, it does nothing. But when the S operate on the 1, this is going to make iota 1. It's going to add just on one phase. Another
Pi by 2.
Exactly. And another T gate, another phase gate. This is actually going to add pi by 4. So this is going to be 1, 0, 0, e power iota pi by 4, you can see here. So this T operates on the 0, it is again does nothing,
0,
but when
0.
the T operates on the 1, this is going to again add this phase.
Pi by 4, 1.
Exactly. So these are the single qubit gates. And similarly, we also discuss about 2 qubits gates. And in the C qubits gates, the first important one we discuss about the C naught. And I told you that all these gates you can construct by this matrix I2, O2, and O2, and unitary matrix U2. And in the case of C naught, this U2 nothing but a NOT gate, correct? Or NOT gate, or simply you can say X gate. So the symbol we use for this is the one node here. So there are two means you can say one bit A and B, and here this plus sign we use. So this is symbol for the NOT gate. And what happens here? This A remain as such, and here it become, tell me.
Sir, please repeat the question.
So what is the output on the second bit?
The second bit, that will be not will.
Sir,
Just
it will be B plus A. No, or
Yes, it is a B
B meaning, yeah.
modulo 2 addition, correct?
Yes, modular 2.
So that is the output, okay, in this case. And of course, the matrix, now you have a task to write down this matrix. In fact, I can tell you, this is a very simple way to remember also. What this does now, I mean, just we are getting too pedagogical now, but see, when you talk about a unitary matrix, so in the case of 2 qubits, so in the 2 qubits, first of all, remember the basis vectors, basis states are nothing but 0, 0, then 0, 1, then 1, 0, and 1, 1. So they are the basis states. And how you can construct this basis states? Very simple. You can take 1, 0 and tensor product of this one. This is what is called a 0, 0 state. And how the matrix is going to construct? Now, this is nothing but a 1, 0 tensor product, again 1, 0. And you know how it will be? It will be a 1, 0, 0, and 0. So this is the one basis vector. Similarly, you can see when you talk about 0, 1, so this is nothing but a 0 tensor product 1. And what is 0? 1, 0, and 1 is what? 0, 1. So this is going to become 0, 1, 0, 0. So you can see this is the, yeah. And the same way you can write down also for the 1, 0, that is going to be a 0, 0, 1, 0. And also for the 1, 1, that is going to be a 0, 0, 0, 1. They're the basis vectors. So when you talk about a unitary matrix, so unitary matrix, that is called I here, it is going to be then 1, 0, 0, 0, and so on. Like this. Now look at, if I give their indexing, okay, so even sometime these states, which is called 0, 0, in the binary notation, I can represent by the 0 number, okay? And 0, 1 called as the 1, and 1, 0 called as 2, and 1, 1 called as 3. And this is very obvious also, no? Because when you convert into the decimal number, binary number, decimal number, so in the binary notation, this is nothing but become a 0 into 2 power 0, correct? Plus 0 into 2 power 1. So this is going to become 0. But when you have a 0 and 1, it means 1 time 2 power 0 and plus 0 time 2 power 0, nothing but a 1, correct? So this signifies now why I'm writing 0, 0, 0 as a 0, but 0, 1 as a 1. Similarly, you can look at 1, 0. It means 0 into 2 power 0 plus 1 into 2 power 1, nothing but a 2. This is why I'm writing 2 here. And look at last one, 1, 1 means 1 into 2 power 0 plus 1 into 2 power 1, nothing but a 3. So this is a 3 actually. So you are converting this binary into decimal numbers. So here, this one is correspond to in decimal 0. This one correspond to 1 in decimal number. This is correspond to 2. This is correspond to 3. Okay. So what it does, the C naught, no? I'm giving you a very simple way to understand, or in this way you can remember, no, in the long term what the C naught gate does. Okay. This is going to change or interchange 2 to 3 and 3 to 2. So the column corresponding to 2 is going to become 3, and the column 3 is going to become, so this is how they're going to exchange. And look at here, this is what is happening. So identity matrix, write down the way it is written. So it is a 1, 0, 0, and 0. So the first one, that is called the 0, it remains same. Then 1 also remain the same, 0, 1, 0, 0. Now you can see that 3 and 2, they will exchange. So here it will become 3 and here it will become 2. So 3 nothing but a 0, 0, 0, 1, and this is nothing but a 0, 0, 1, 0. So this is the matrix. No? Technically, what are you doing? You are converting 1, 0, okay, to 1, 1, and 1, 1 to 1, 0. And this is what the C naught gate does, no? Because this is the XOR. So XOR, what it does? So for example, if this is, let us say 1, and this is, let us say 0. So for example, this one, okay. So you have when you have a 1, 0, what we will do? So control bit is going to control the target bit. So if the control bit is 1, what it will do? It will change the target bit to, it will flip the spin of the target bit. So this will become 1, 1. And similarly, if you have 1, 1, so what will you do? It will going to make
1, 0.
1, 0. So you can see it is going from 2 to 3 and 3 to 2, like that. So this is a very simple way to remember what the C naught gate does. So in long run, if you are doing some course on the quantum computing, then these tricks will be very helpful for you. So these are the C gate, and then we discuss about the second one is the C Z gate. And what this C, now the same logic I can apply here. You can see the CZ gate. No? So in this gate, you can see that this U2, nothing but a Z gate, correct? And Z gate क्या होता है? It is a 1, 0, 0, -1. So the matrix become what? Look at this is become 1, 0, 0, and 0. 0, 1, 0, 0. Okay, so that is the like this way you can say this is the matrix is nothing but a I2, O2, O2, and U2.
U2.
So I2, and this is 0, 0, 0, 0. So here is also 0, 0, and 0, 0. And this U2 is become Z. So this is going to be 1, 0, 0, -1. So that is the CZ gate. And how to represent circuit diagram is this one. So node here, and here it will be a Z, and like this. So this is the input A, this is input B. So what is doing it? It will simply going to change. Look at here. This is the 0 based column. This is the 1 column to 1 corresponding. corresponding to column, and third, and like this way. So what this does, this simply going to make 3 to -3, correct? Technically, if you have 1, 1, so the CZ gate, when you're going to apply, what you will get? -1, 1. This is what Z gate do. Z gate is going to simply, it does nothing on the 0, correct? 0 remain the 0. Look at here. 0 remain 0, but 1 become 1, 1. Okay, so when you're going to put Z here at this location, okay, then this is going to cause only the third column, okay, become minus, okay. Other columns remain unchanged. Nothing changes to other part, okay. So it means that when the CZ is going to operate on, let us say, 0, 0, it will do nothing. It will remain 0, 0. When the CZ operate on the 0, 1, it will do nothing. Okay, like that. So आप अपने आप try to do yourself. I'm just revising this topic. So third part, C phase gate. And the C phase gate means you're going to now use the S phase, correct? So here the U2 will going to be S. And what is S here? 1, 0, 0 iota. So the C phase matrix is going to become, look at I means 1, 0, 0, 1, and then 0, 0, and then 0, 0, and this is going to be 1, 0, 0 iota. And you can check what it does. Okay, so the symbol is similar. The symbol is again, this is A qubit and B qubit, and here it is going to be a node, and here we going to use the S. That is, and what it does, again, look at the S gate. What S gate does, it is going to do the same task here. No, look at here. It is just it does nothing on the 0, but it's going to make impact on the 1. So it is going to make I1. So that is the task here. So it is same like a CZ. It is going to make 3 to I3. Means if you have 1, 1, and when you apply the C phase gate, it is going to make I1, 1. So these 3 gates you can think about. And one more gate we discussed, fourth one, very important, that is called the swap gate. So in the swap gate, the bits are going to exchange, okay? So the symbol we use, this one. So this cross and this cross. So you have a A here, you have a B here, okay? And then after the swapping, it is going to become A, this is going to become not A and B. So what happens here? It changes everything. I mean, so when you're going to apply the swap gate on, let us say 0, 1, it is going to make 1, 0. Of course, nothing happened to 0, 0, but in the matrix form, you can see that it's going to make an impact. So the 1 is going to become 2, correct? That's all. So here, this is going to become then, this is the 1 matrix. So 1 become 2, 2 become 1. The 2 will come here and 1 will go there. And the rest remain the same. And see. Then let's go quickly then, because this is just a revision. So now you have a 3 qubits also, 3 qubits gates. And in this, I discussed the first, the important one is the Toffoli gate. And to make this one, again, you can see, you can make I4, O4, O4, and U4. Okay. In the Toffoli gate, this U4, nothing but a C naught. So you can see, I mean, you can write down the matrix yourself. So this is going to be I4, O4, O4, and this is going to be a C naught. And this is a 8 cross 8 matrix. You can write down yourself. But symbols is this one. Now this is 3 qubit gate. So you have a A, and then you have a B, and then you have a C. Or maybe I think better to use like this way. So this is called C, this is called A, this is called B. So there is a one node here, and then this symbol. So, all right. And what it does, if you look at now, I can give you a trick here. So this is called the control bit. And control bit always remain the same. Nothing happened to the control bit. Maybe I can call C1 and C2. This will be another control bit. And then you have a target bit here. In Toffoli gate, I think this is also another, there are two nodes. So the another node will be here. So the C1 remain the same, C2 remain the same, and this B will going to change. The target bit going to change. So what happens here? When the C1 and C2, they are 1, 1. Okay, so for example, let us say this is the 1, this is the 1, and this is 0, then you will get 1, 1, and this is going to also become 1. The spin going to flip based upon the value of the C1, C2. So in this case, if you look carefully, the simplest and shortcut way to remember is that here the 6 column and 7, they're going to exchange, meanings 1, 1, 0. Look at here. This is going to become 1, 1, 1. Or maybe 1, 1, 1. This is going to become 1, 1, 0. So this is the Toffoli gate. And the second one, the Fredkin gate. So here this U4 is nothing but a swap. You can see the matrix become I4, O4, O4, and there is a swap matrix here comes out. And what it does then, you can see you in this circuit diagram is one is a control bit, and then so this is going to swap actually. Okay. This is going to swap A and B. So depending upon the C value, the A going to become B and B going to become then A. And again, this is the 8 cross 8 matrix. And if you look carefully, then here again, the 5 is going to become 6 and 6 is going to become 5. For example, let us say 1, 0, 1. This is the 5. This is going to become then, because look at the control bit is 1. And then these two bits will going to exchange 1, 0. And if you have a 1, 1, 0, again, you look at the control bit. That control bit going to cause this target bits to be exchanged. So 1 is going to become 0, 1. So 5 and 6, they are going to be exchanged. So these are the gates we discussed in the last class. So in today's lecture then, we will focus two things. A major task is to discuss about the quantum algorithms. But before going to quantum algorithms, so I can also discuss about the quantum circuits. Just a minute. So
do we have gates for 4 bits, 5 bits, and
yes,
so on?
yes, very difficult to realize. Yes, there are, but generally now these 3 qubit gates, 2 qubit gate, and 1 qubit gate, they going to give you the universal gate. Means using this no 2 qubit, 3 qubit, and 1 qubit, you can make a universal gate. It means you can realize all types of algorithms. So there's no need technically to go for the higher orders. No,
So the
gates.
higher orders can be broken to lower orders.
No need to go for that. I mean, it's become complicated. I mean, because universal gates you can construct easily with the these gates.
Okay.
It's like a NAND gate. Okay. So once you have a NAND gate, there's no need to construct other gates. Okay. You don't need to use other gates actually. You can construct every algorithm or using a NAND gate. So this is what true for the same case here as well. So see, the quantum circuit technically is just a basic model. Okay. And how to arrange these gates and how these gates are going to apply. Okay. So I will give some example and we will try to solve some problems also, because finally you have to also appear in the some quizzes. So the problems now will come from these sections also. So as I mentioned that the quantum circuit is like you can also think like a recipe. Okay? That tells you how to process the quantum bits step by step using the quantum gates. So for example, but first of all, I will give some properties just for the sake of completeness. So the first property that the quantum circuits are reversible. Okay. So reversible means if you know the input, then you can also get the output. But if you know the output, you can also get the inputs, which is not true in the case of classical gates. So for example, in a classical gate, think about the situation that AND gate, and you have a 1, 1, and output is 0. Output is 0. And just by knowing 0, you can't reconstruct the input. Input can be anything like 0, 1 also, and 1, 1, 0, 0 also. So if you know the output, you can't construct the input. But in the quantum gates and quantum circuit, nothing but a quantum combination of quantum gates only. Okay, so they are reversible in nature. So all quantum gates are reversible, and you can think about also now Hadamard that blosphere. So blospheres, if you think carefully, then you can even imagine that the why these gates are reversible, because technically what these gates are doing, okay, they're going to rotate this vector on the sphere. So when the vector is going to rotate on the sphere, so for example, you have a 0, then you can bring to 1 by pi rotation. So pi by 2 and pi by 2, you will be here. Again, you take pi rotation, you again go back to 0. So if the vector is there, so this vector can rotate and it can go here also. It can again go back to the same location. So this way you can see that all gates are reversible. Even Hadamard gate, when I say all gate means all gates are reversible. Second, fan in and fan out are not allowed. Fan in means you have many inputs, and many inputs give only one output. And fan out means you have only one input and gives many output. This kind of possibility doesn't exist in the quantum system. Means you have a 3 qubits in the input and 1 qubit only at the output, and vice versa. This is not true, because here when you're saying 3 qubits going to 1 qubit, then technically you are destroying the qubits. And remember, qubit neither can be created nor can be destroyed. Okay. So when you have a 3 number of qubits, they will remain 3 in the circuit, okay? And if you have a 1, it will remain always 1. You can't create. So here you can see that you are creating. So here qubits are created from 1. So from 1 qubit, you're creating a 3 qubits. And another very important that measurements of a quantum circuit. So when you talk about a measurement of quantum circuit, so this measurement is not reversible. Measurement is not going to be reversible. Operation is reversible, okay? Superposition, till superposition is reversible everything. So when you do the measurement, so for example, you have a psi A time 0 and B time 1. And once you do a measurement,
it collapses to
exactly.
state.
So this is going to collapse to either 0 or collapse to 1. So it is no longer reversible. So either you will get 0. If you get 0, you can never reconstruct back. So here in the quantum system, only thing which is fixed in the measurement is the probability. So the probability of getting 0 will be equal to what? A square. And divide by A square plus B square. And the probability of getting 1 is a B square and A square plus B square. So only these terms are fixed. Okay. But remaining is going to be destroyed completely. Now in the quantum mechanically, how we do, no? For everything there is symbol. So there is symbol here also. So in the box, you show this kind of scene like a meter with a needle like this. So at the input, you have a qubit. And at the output, you have the output value, which we show by 2 lines, okay? So because see, once you do the measurement, you get the classical value. So once you do the measurement, whatever you have now is a classical number with you. So here at the output, we're going to have a classical bit. And this is the measurement. So this is the symbol we're going to use for the measurement, okay? This is symbol for the, I can say, symbol for the measurement. And remember the single line. So you have a single line and then you have a double line. So single line representing the qubit and double line representing the classical bit. Or you can say single line represent quantum and double line represent a classical. So quantum measurements are not reversible. Okay. Then how to use them? Okay. So for example, when you actually going to draw or apply the qubits, so you can apply in 2 different sequence. Okay. So one is called quantum gates in series. So you can apply these quantum gates in series. So when I say series means, for example, when I was talking about this rotation, no? So you have a matrix, I mean, a 2D space. And in 2D space, let us say you rotate the system along this direction. And for this rotation, you have a one matrix, let us say called T1, which I denote by 1, 1, minus 1, 1. Now, similarly, after rotating about the anti-clockwise, again, I can rotate clockwise. Another matrix will come into picture. So what you're doing first, you're doing this and this. So these 2 operations are in series. So maybe I have a vector here. Let us say this is the vector I'm talking about, and I want to see where it will go. Let's say R. So what I will do, I will going to apply first T1 on the R, and whatever result I get, I'm going to apply the T2. So this is the example of a sequential operation of any operator. Okay, this is the what is we call in linear algebra as a transformation, or you can also call it the linear transformation, because the grid lines always remains parallel. So as long as the grid lines remains parallel after the transformation, then such transformations are known as the linear transformations, and that whole algebra comes under the branch we call as the linear algebra. So here also you can apply a gate. I'm audible to all of you?
Yes, sir.
Good. So let us say you have an input bit is on this side. And you apply first, let us say gate A. Then you apply, let us say gate B. And let us say here is a psi final. So in circuit symbol, I can represent like this BA. I will show like this. Okay, but what it represent? It represent that the B, I mean A is going to operate first on the psi, and that is going to give me the psi f. So this is how we can understand. Okay, for example, think about the case if you have a 0 here, then I will say, and okay, let's take a real example. So I have a y here, then I have a x here, and I want to see what will be the output. So this is equivalent to a 0, and here it will be a xy. Okay. Technically, it means xy operates on the 0. So what you will get? Any idea? What I will do to the 0?
First, y will operate on the 0.
Yes, y operates on the 0. It will make iota 1, correct?
Yeah.
So this is going to be x into iota 1. And this is when x operates on the 1, what it will make? 0, correct? So this is going to be iota.
Iota 0.
Exactly. So, or maybe like again the same thing, no, in the matrix. Okay. In the matrix also you do the same thing. No, you can multiply these two matrices and then you can operate, or vice versa, whatever the way you like. Okay, both are the same. Similarly, let us say if you have 1 and this 1 operates by y and then operates on the x, can somebody tell me what is the answer finally then?
Minus iota 0.
Minus iota 0, is it? 1 iota, correct? Because when the y operates on the 1, it becomes minus iota 0, correct?
Yes.
And when the x operates on the 0, it is going to make 1.
1. So minus iota 1.
After all, you also appear in the some quizzes and final exam. Your certificate will be given to you only when you get some marks. Okay. So try to revise these topics also and do some mathematics. You already have a book, correct?
Yes, sir.
So similarly, there's another symbol we're going to use. That is this one, I. Okay. This is called NOP gate. NOP means no operation gate. Like same way in the matrices also, no, we call identity matrix, correct? 1 0 0 1. It does nothing. So same way here also, when you are psi I and when you pass through I, you will again get the psi I. So this is called the NOP gate, NOP gate. So now let us try to take some examples, just to make you feel comfortable that how these quantum circuits are working together. Okay, before I go to second case also must discuss. So one is the quantum gate in series we discuss. Now the second is the quantum gates in parallel. So let us say again, I can assume A and B are two single qubit quantum gates, and the one qubit is psi1, another qubit is a psi2. And if you have a like this situation, okay, then what is the resultant output here? So psi final. So now we will say these gate operations are in parallel. So we represent this like this way. Now you are in the, now look at this A is a single qubit gate. So A and B both. So I can say A and B both are a single qubit gate. So when I say single qubit gate means what is the matrix dimension? 2 only, correct? So it's 2 by 2 matrix. But when you going to deal with 2 qubits, okay, then the dimension will going to become a 4. No? So here it will be also the gates also going to have a tensor product. And now I will show like this way. You have a first qubit and then second qubit, and then I will show the outputs. Mathematically, we're going to represent like this way. So look at here, when you have this in combination in parallel, okay, then the states are also going to have a multiply because they are from different Hilbert space. Psi1 belong to one Hilbert space because this is, look at this is electron number 1 and this is electron number 2. So they are belong to the different qubits, okay, Hilbert space. And when you're going to multiply, then they're going to multiply through a tensor product. So this is the resultant psi1 and psi2, and here also A and B. So this is how you will get it. Or maybe I can write like this way, A tensor product B. And generally, when you have a tensor product of these two states, then I can also write like this way also. It is the same thing. Even sometime we can write like psi1 and psi2. It is the same thing. Okay, but keep in mind that this is the tensor product. So for example, think about, we have a example we can take. So I want to apply Hadamard gate. So you have a 0 state and I want to apply, let us say, Hadamard gate here. And on the one state, do nothing. Okay, this is still a parallel combination, but now the 2 qubits are there. So in this case, because there's no gate in the one, to do the calculation, what I will consider myself here NOPE gate, correct? And make sure that this is the most significant bit and the least significant bit. And in this case, the first one, the most significant bit will come first, and tensor product of the second operator I, this, into this tensor product 1. Or maybe I can write like a H, I, and 0 and 1. Now you see what this H, I is. Okay. So what is H? 1 by root 2, 1, 1, 1 minus 1. And tensor product, what is I? 1, 0, 0, 1. So this is going to become a, now this is 2 by 2 matrix, and now I'm going to get the 4 by 4 matrix. So this is going to become 1 by 2. You can see 1 multiplied, it is going to get the same quantity again, 0, 1, and 1, 0, 0, 1. and 1 0 0 1, and this is become minus. So minus 1 0 0 minus 1. So you can see that that is the term here, this quantity. And what is this one? 0 1 0 1, nothing but a 0 1 0 0, correct? So you can see that now that you have a h I and operating on the 0 1. So you have all these matrices, and when you solve it, you're going to get 1 by root 2 0 1 0 1. Now look at how I can just simplify this one also, because this is 0 1 0 1, so 1 by root 2. So technically this is going to become a you see here, when I say 0 0, so 0 0 is nothing but a 0 of 4 0, and when I can say 0 1, then 0 1 0 0, so on. So I can break this in two parts. So this is going to become 0 1 plus 1 1.
So Sugam, 0 0 has a 1 in the first element, no?
Yes. Thank you. Yeah. So this is the what is the state? Again, a
Bell
superposition
state.
state.
Bell
Is again,
state.
no, this is not a Bell state.
Sorry, no. It's 0 0.
Still, you can write this as the tensor product of two states. How I can do? Look at 1 by 2. I can write like a 0 and 1 and tensor product of 1, correct? Because when this comes here, it again becomes 0 1, and when this comes here, it's become 1 1. So if you can write a state as a tensor product of two states, then such states are simply called the superposition states. They are not going to call as the Bell states. Bell state, remember, mathematically Bell states means entangled state, and it defined as like this: if the state cannot be written as a tensor product of the two states. So I given you the example like 0 0 plus 1 1. So whatever you do, you can never write this as a tensor product of the two states. Not possible. So this is a Bell state, but this is not a Bell state. So this is just creating a superposition state. This is a superposition state, but of course not a Bell state. So this is how I'm just giving you some example that how you can now solve these problems. For example, see, if you want to create Bell state, I think I given you example. If you want to create Bell states, what you can do? I can let's take one circuit diagram and one state here, and then I apply a here a C NOT gate. Okay, this is the most significant bit and least significant bit. So now see, this is also a circuit diagram in the parallel. So here what will happen? See, H is going to act first. Okay, so in this case, again, just to make the simplicity here, because nothing acting on the I in parallel to H. So I will put I here. Then this is going to become H tensor product of I. And the combination of these two are nothing but a state called, let us say 0 1. So everything is going to act on the 0 1. And here you're going to have a C naught. So be careful that this H is the 1 qubit gate, and the C naught, this is C naught, this is a 2 qubit. So they can't multiply, no, through a tensor product. So in this case, this H and I we can combine, and can somebody will find what is the value you're going to have here? Or maybe simply you can go one by one also, okay? So you can try to find out the wave function here, state here. So state here will be what? This is going to be a, let me call psi1. So the psi1 will be nothing but a H operating on the 0. I mean, you can do this one also. You can write down the matrix here and then apply on the 0, 1, okay? Or you can go step by step also. So when I go step by step, then I apply first S0, then it's going to give a √2 and 0 and 1. Okay. And there here is a 1. Okay. So it means the wave function here. Now combine wave function. Let me call that as the psi in. So the psi in will be equal to psi1 and tensor product 1. So this is nothing but a 1 by 2, 0 and 1 and tensor product 1. So this is going to become 1 by √2. It is simply a 0, 1 plus 1, 1. I mean, this is what we also did in the previous one, no? Here. So up till now, up till this location, we are the same like the previous one. And now on this state, you're going to apply the C naught. So the C naught is going to apply on the state called psi in. It means C naught going to operate on the this state. That is the 1, 0, 1 plus 1, 1. So what will it do? Now look at 1 by 2. So this is the control bit. So control bit is 1. So this is going to make it control bit is 0. So this is going to become 0.
0 and next is 1, 0, 1 and 1, 0.
1, 0. Correct. And this is a Bell state because you cannot write this as the tensor product of any two states. Not possible. So this is the Bell state. So this way, what I will recommend you, please, I will share your notes where lots of problems will be given to you, okay? And you try to solve. I mean, so there can be many different types of possibilities. For example, even I can apply hard mod gate later on, and then C naught gate the first. Then what will be the output? So these kind of combinations, now you must try to do yourself. There can be many possibilities, like think about you have a 0 and then I apply H, then again 1 or maybe 0, and then apply, let us say, X, any gate, and then apply this gate. So try to solve first up till 2 qubits, and slowly, then you can go to the 3 qubits also. You can apply the Toffoli gates. You can apply the Franklin gates. Okay. So even you can think about like A is let us say H here, and let us say Y here, and B, and then here you can apply a Z gate. That is called CZ gate. Okay, I hope these kind of practices you will do yourself. And with this, then I think we can formally come to our next major topic we have to discuss today, and that is called the quantum algorithms. But if before I go to the next topic, if you have any questions or doubts, we can discuss. So quantum algorithms, I discussed the, for example, there are many, okay, but I will focus on the first very basic and the first quantum algorithm, that is called Dutch algorithm. And here actually you will see, for example, many days ago you asked that key how these interference work. How I told you that if I'm going to add, let us say 2 plus 3, then the possible answer will include everything. Okay, it is 0, 1, 2, 3, 4, 5, 6, 7, and so on, depending upon how many qubits you are using to write down the 2 and 3. So if you take only 2 qubits, then this possibility will go only to 7. But if you take 3 qubits to represent these number 2 and 3, then the possibility can go from 0 to 15 and so on. Okay, it is simply like 2 power 2 and 2 power 3, like that. And 2 power, no, it will go like this. 4, 8. Okay, let's not make it too simple. But then I discussed that in that lecture that what we do, the answer is 5. And you have to write down a program so that the probability of the 5 goes higher. So remember that when you talk about superposition, so in the superposition state, there are many types of waves will going to be there at the same time. There are many waves will exist. Okay, so another wave like that. So each color is representing, let's say here is a one type of result, and let us say that this 5 is the red color. Then when you do the superposition, okay, then the probability of the 5, okay, will become higher, and the probability of the others will be going to be very small. They will be there, but the probability is going to be very small. So you can see that when this 5 result will be going to now show up. So you have all possible probability waves, and then in the quantum superposition, you're going to increase the probability of the one answer, that is the right answer. And your question was that key without knowing, okay, key what is the right answer, how we can increase the probability of is finding. So this is something we will discuss in the Dutch algorithm. Of course, I'm not discussing the sum here because the Dutch algorithm has a different task to do. Okay. So the Dutch problems, no? The Dutch problem actually what it does, I mean, this is actually algorithm to find whether Boolean function is balanced or constant. So when I say constant, so constant means whatever I put in the function, it gives the same output. So for example, if I put, let us say 0 and you get answer, let us say 0. If I put, let us say 1, again you get 0. Or it can be, if I put, let us say 0, then you're getting 1. If I put 1, again you get 1. So if you are getting the same answer, okay, then I will call this as the, so my function fx is a constant. But let us say if I put, let us say f0, the function becomes 0. If I put f1, the function become 1. Or if I put 0, function become 1. If I put 1, function become 0. In that case, I will call the fx is a balanced. Okay, the terms used to represent. Okay, so this Dutch algorithm is actually was the first algorithm. Okay, this was developed to prove that quantum computations takes less time than classical computation. So the purpose was the Dutch algorithm. This is not practically no, usable algorithm no, in the laboratory. This was, I can say, a kind of no, a proof to show that the quantum computation is faster in comparison to the classical computation. So for example, if you want to check classical, so if you have a classical computer, and if you want to check whether the function fx is a constant or balance, then what is the first step? So step number 1, I will put some value, let us say f0, and let us say answer is coming 0. So this is the first step. I will first put, these are Boolean functions, I will going to first put x equal to 0, and I will check what is the value of function. Now the function value is 0, but this first step will not going to tell me whether the function is constant or balanced. I have to go for the step number 2. So in the step number 2, I will put 1. Now, if the putting 1, if it's become 0, then only I can say the function fx is constant. And if it is become 1, okay, then this combination will give me that the function fx is balanced. So doesn't matter what to do. I mean, whether function is constant or balanced in the quantum system, you can see in the classical system, you have to do 2 steps. And this is what the Dutch, the scientist, he proves that in the quantum algorithm. So in quantum algorithm, only one step is required to prove check whether fx is constant or balanced. I hope this is clear. The purpose of the Dutch algorithm clear to everybody?
Yes, sir.
So this we will do. We will check how it is done. Okay. So first of all, let me tell you the quantum circuit for Dutch algorithm. So what it includes? This includes let's say 2 bits. It can be multiple bits, and so on this bit you're going to apply first is the hard mode, and then you have 0. So first here you're going to invert. So you apply X. So what this X will do?
Well, just not
It will
operation,
not get. It
flipping,
will simply going to make
flipping.
0 to 1. Okay. And then the second step is that you apply hard mod gate in parallel. So technically, I'm applying hard mod gate on both the states.
Yes.
So here you will have a one state, and it will going to produce a superposition state, and then this is going to fed, okay, into one oracle. So in the oracle, this is going to be input X. So X is the input. So here I can say X, I mean, it is a binary input. And this Y is also a binary, but we call this as the auxiliary qubit. And then, so this is a Y, and this oracle is actually a gate. I can call either UF. So nothing happened to the X bit, but this Y bit is going to change in this format. So the output at the second qubit will be this much. Then you're going to apply one more hard mod gate at the output of the X, but do nothing on the second qubit. I mean, after this oracle, second qubit doesn't play any role. The role of the second qubit, which is called as the auxiliary qubit, is only used up till oracle. Okay. After the oracle, there is no use of the second qubit. And then you're going to produce, apply a hard mod gate. And after that, you're going to do the measurement. But you do the measurement of the first qubit only. You do the measurement on the first qubit only. And this output, now remember that is the most significant bit. This is the least significant bit. The output of this first qubit, if this comes out to be, let us say, 0 state, okay, then I will say the function is constant. If the output collapses to 1, then I will say it is a balanced state. So see, without knowing the type of the function, I can just look at the output. If the output becomes 0, then I will say it is a function is a constant. And if it is 1, then the function is a balance. And we will see how it works. So the steps are what? Okay. So so let's look at the steps. Then I will now first let's understand what is happening here, step by step, and then I will discuss in detail. So in the step, the first thing that prepare initial states. So finally, initial state, you can see here at this location. So now this become 1. So technically, this is going to become 0 and tensor product 1. This is nothing but a 0, 1. So technically, when I say prepare initial state, I means I want to prepare 0, 1 state. Then the second step, or you can also write like a 0 tensor product 1. So you have to prepare this state. Then second step is the apply hard mod gate to both qubits. So this is going to create, so this creates, tell me what this will do. It will going to create a superposition, correct? It means this H operating on the 0, it is going to give 1 by root 2 and 0 and 1. And this state is also called as the plus state, correct? This is the hard mod basis state. And when the H operates on the 1, this is going to give a 1 by 2, 0, minus 1. This is also called the negative state. So you apply this hard mod gate on both, and this way you can create superposition states. Then third, so at this location, you can see here, at this location, which state you have? You have a plus tensor product negative. So this is state you have at this location. And after this, you apply, okay, oracle. So then you're going to apply this UF on the state, which generally actually equal X and Y. I mean, here it will be a plus and minus. And what this oracle will do, this will not change the X state, but the Y state will become Y modulo 2 addition of function fx. So what this oracle does here? So this oracle actually encodes the function fx with the qubits. So this oracle is going to encode the function fx with the qubits. So I will discuss about this further. I mean, you can think it is like a magic box, okay? And that magic box is going to have a rules for the functions. And your task is just simply is to figure out something about that rule, no? By asking question. My question will be here what? I will ask this oracle, tell me whether the function fx is a constant or balance. And accordingly, I will tell you how it does all the calculations. So this is the next step. Then the fourth step. After this, you get the output. You are here now. So you can see this is the step number 1. This is step number 2. And after step number 3, you will be here. And now you're going to apply the step number 4. And what is step number 4? Just apply a hard mod gate to first qubit again. So you have to apply this hard mod gate again, but on the first cube only. And this is the very important step because here, okay, this step actually causes interference. But of course, it will, what kind of interference it will be, it is completely based on the function fx. And look at what is the last step. So now you are here. After the measurement, after there's a interference, you will be at the step number 4. Now this interference, okay, is going to enhance. Remember, at this stage, the probability of a right result will be enhanced. So at this stage, I mean, so before, when you do the oracle, okay, so see, in the oracle, it will going to create a superposition of the all possible answers. So answer is already done here, okay. All the query has been done in this stage. So whatever the arithmetic you want to do, this arithmetic has been done in the oracle. Oracle, as I mentioned, you know, key oracle is the box where you will ask your question. So this oracle will tell you whether the function is constant or balanced, but it will tell both the answer. Okay. It will give you both the answer. Okay. It will give you the answer 0 also and 1 also, but only after the interference, the result of the right answer will be enhanced. And then you going to do the measurement. And once you do the measurement, now I can see here 2 lines, no? Because this is the quantum to classical. So when you going to, or maybe like this. So after the measurement, the wave function going to collapse. The wave function will collapse to one state. Of course, the probability, which is going to have a higher probability. So the last step, the step number 5, is nothing but the measure first qubit. So you have to measure the first qubit. That is the last step. And you see if output state is 1, then I will say the function is balanced. If output state is 0, then I will say the function is constant. So you can see that this is the overall, okay, this is the overall steps in the Dutch algorithm. So you are going to go through these 5 steps, and I will discuss these 5 steps in detail now, okay? But please have a thorough clarity that what are the steps are involved in this Dutch algorithm. And then it will be much easier for everybody to understand each step and what is happening in the each step and how it is happening. That is also going to be clear.
What is the interference in between?
Coming, yes. Coming to this part, this will be interference. I mean, in one line, I can tell you the interference between the state 0 and the state 1. Okay.
So basically an interference between all the possible results.
Exactly. And there are only 2 possible results here, 0 and 1, correct?
Thank you.
So you have only 2 possible results. So this is interference of 2 states only. Anybody else want to ask any question?
Yeah, this interference concept is not.
Yes,
clear.
exactly. That
Maybe
will.
it is coming.
Yes,
Yes.
exactly. I mean, I
Yeah.
just discussed the steps only. Now
Yeah,
let's
because-
come to then.
Yeah. So the
Okay, let's-
interference. Sure. Please go ahead. Go ahead.
Okay, so let's start then. Okay, so let's go in details to understand everything in detail conceptually. So when we talk about step 1, so we are preparing the state 0 at the input, and then the state is 1, correct? And you can see that this 0 state and the 1 state. And I'm going to apply the Hadamard gate on both. So at here, the state will be then, this is going to become which state? Plus, and this is going to become
Plus.
minus. So at this location, if I write down the combined wave function, so this is going to be a tensor product of these two. After this, I'm going to put into the oracle. So before I put this into the oracle, let me also explain you one concept that is called the concept of phase kickback. Mechanism. So we'll understand now. See, this is X and this is the Y, and you know that when the oracle is designed in such a way that when it is going to act on the state X and Y, means these two states, it will produce what? It is going to produce X as such, and Y is going to be Y modulus 2 addition of function fx. Now see, I'm just taking one special case, okay? What happen if I apply UF on X and a negative state? And I want to prove that, no? I mean, look at here, this is X, and what is Y here? Negative, no, correct? So I'm keeping X as a general, and I'm putting Y specific. The Y is negative. So I will keep Y as such, and now the product here. So if you look at here also, although I mean at this location, it is nothing but X input Y, nothing but X and negative. So I'm trying to look at what this oracle will do when it's going to act on these two inputs, this and this. And I will prove that this is going to be actually equal to -1 power fx and X and tensor product negative. So this is the one result which I want to prove. Okay, so let's prove this. I have written, but I can prove it. So you can first of all see what happens when I multiply X tensor product with a negative. I will keep this negative. I know what is 1/√2. I will keep X as such and tensor product, and this is going to be nothing but a 0 and -1. Then multiply, this is going to become 1/√2. So this into this is going to become X and 0 minus X into 1. You see here. And now I want to apply this UF on X and negative. Now see, it means this will go inside. So 1/√2 here, and look at here. It means UF is going to apply on the X and 0. And this UF also going to apply on the X and the 1. Please be attentive here, no, because step by step, these steps are very important to understand and keep clarity in the mind to understand this interference, which is going to come in the next step. Now see what this UF will do. Look at here. This will going to cause X will remain as such. And here this Y is what? 0, correct? So what you will get? See, Y is 0. So this is 0 modulo 2 addition fx. Correct? minus. What will happen here? X state remain as such. And here, this y is 1 modulus 2 addition fx. Now see, this function 1 modulus 2 addition fx, what it will be? Now I can directly write this as a 1 minus fx. Why I'm saying? Because see, this fx, let us say fx can take two values only, okay? So it can be either 0 or it can be 1. Now see, if I take 1 modulus 2 addition 0, what I should get 1, correct? But if I take 1 function, then this is going to be a what? Tell me.
0.
0, correct? So it means it's a correct expression, because in this equation, you can see if I put fx 0, then I will get 1. If I put fx 1, then I will get 0. So you can see that this final answer will be only x, and this 0 doesn't mean any. So this is going to be fx as such.
Sir, one
And
question.
just a minute. And this is nothing but a 1 minus fx. Yes, please.
The question is for binary addition. Due to binary addition, 1 binary addition 0 is going to be 1.
Exactly.
But 1 binary 1 that is giving 0, it I can understand this thing. 1 binary 1 binary addition plus 1 is
It gives
0.
the 0 with the carry 1.
Yeah, exactly.
Oh, actually for the carry, okay. We
Yeah.
are taking the most significant bit
Exactly.
over here. So okay. Thanks.
Okay.
Thank you very much.
So this is the function you have now here. And look at carefully now. I want to prove what? I want to prove this quantity. And you see, this is getting proof from this equation. So look at here, if function fx, let's say it is 0, okay, then what I will get? I will get 1 by root 2. This answer will be what? This is going to be a x, and this is going to become then 0, correct?
Yes, sir. 0.
And minus x, and this is going to become 1, correct? And here I can take x common out, and tensor product 1 by root 2, and this state nothing but a 0 and minus 1. And you can see this is nothing but a x tensor product negative, correct? So you can see that nothing happens. This state UF is acting on the x negative, and you get the x negative back. So there is no change here. Now look at, if fx is 1, so in that situation, this function, the output here, and now here it will become 1 by root 2, and this is going to be x, and this is going to be 1 minus x, and this is going to be 0, which can be written as I can take x common out, and tensor product, this is going to be 1 by root 2 and 1 minus 0. And this is nothing but a x. I can take minus out, then this is going to become minus sign here. Keep it in mind, minus sign, or like this way, minus x modulus minus. Are you getting this two parts? So you can see here, there is a change in the sign. It means when I'm writing this equation UF acting on the X, tensor product negative, and writing like this way, minus 1 power Fx into X, and this, nothing wrong in this, because you can see here, if Fx is 0, then this is going to become simply X and minus. And if Fx become 1, then this is going to become minus tensor product, correct? I hope it's clear to everybody. This is how I can write down this operation. I need your feedback now, because after this, the things will become a little bit more complicated. So up till I think here, we should be clear. I'm just doing some mathematical manipulation. I'm trying to give one simple mathematical equation where I'm saying that, now look at, from here, what are you getting? When you're going to apply this UF on X and Y, then I told you earlier also, when you talk about Oracle, what Oracle does, Oracle encodes the function fx with the qubits. So you can see here, this is what it's doing. So when you're going to apply Oracle UF on the XY, it is going to encode this function with the qubits, and particularly with the first qubit. So this UF encodes fx with first qubit in the form of phase, like 1 power fx. So this is a kind of phase, okay? The phase means it can be, phase will change, then value become plus or minus, okay? So you can see this Oracle is going to encode this function with the first qubit. Please let me know. Is it clear up till here?
Yeah.
Good. Now, coming back to our diagram, which we had. So it was H, or maybe I can simply say this is the 0 and this is 1 also. That's also fine. And this is X and this is Y. And here what I'm getting now. So after this, I will apply H. So after the Oracle, you are here. And at this location, this is nothing but a plus and negative. Or maybe, so what going to happen here? So this is my function, let us say psi 1, okay? So it means this Oracle, so this psi 1 is this much. So what I will do, I will just keep this y as such, and let's open the plus sign. Okay, so plus is nothing but a 1 by root 2 and 0 and 1 and tensor product negative. What it will give you, look at here. This is going to be 1 by root 2. And this becomes what? This becomes 0, tensor product negative, plus 1, tensor product negative. So this is the function at this location. That is a psi 1. And now I'm going to apply the Oracle. This Oracle going to apply on the psi 1 means this Oracle is going to apply on this state plus and negative. in principle, this is applying on these states, means I will take 1 by root 2 out, and I will take this UF inside, and inside this is acting on the 0 tensor product minus, and then it will act on this state that is called 1 and tensor product minus. Fine. And you see what it does. No, look at here. I already told you that when this UF is going to act on the X and negative, what will it make? Minus 1 power fx, and X and the negative will come as such. So it will going to make this one. Look at here, 1 by root 2. Look at here, X is 0. Okay. So what it will going to give? It will give minus 1
just
power.
1.
No, it will, no, X will go inside, no, function, inside the function, correct? So this will become F0, correct?
F0.
And here you will get X as such, but X is 0. And tensor product negative. Look at in the second step. It is going to make minus 1. Now X is 1. So this is going to become F1. X as such and minus also as such. So you can see that this is the outcome when the oracle is going to act on the psi1. Now here I can take minus out from this whole equation. So this is going to become 1 by root 2 minus 1 and F0 and 0 state plus minus 1 F1 and 1 state tensor product negative. All right. So you can see that this negative, the second qubit, na, correct here. So this is the second qubit after superposition. And this one was the first qubit. This whole thing is the first qubit. So you can see very clearly that this oracle is actually encoded the function fx entirely as a phase on the first qubit. तो अच्छा तो लिख भी सकते हैं यहाँ पर. So the function fx, okay, is encoded entirely as a phase on the first qubit. Okay. And here the second qubit after this second qubit after this becomes irrelevant. And this mechanism, the first one, this one is what is called the, I mean here is called the quantum parallelism. Quantum parallelism. So see, you are doing only one step here. There's only one computation. And both values are evaluated in one call. So unlike classical mechanics or classical computer, here in a one call, both the answers are available with us. Now after this, we will do superposition and we'll see which answer we're going to get. I'm going to get two answers, either 0 and 1. And you can see the 0 and the 1, they are already there. But with the phase, okay, this is the phase factor. Now, after this, then the magics happen now here. You're going to apply the Hadamard gate. So this is step number 3. Apply H gate again on the first qubit. And this is the magic. Now in the if you feel that something magic happens here, so yes, magic happens here only. Okay, that is nothing but a quantum interference. So see here, now what I can do, I can write now this function whole as let us say I can write whole this function. Now this is one qubit function. I can call it, let us say phi, and the second one keep as such, like this way. So see here, this is the second qubit and this is the first qubit. The first qubit is in the superposition. I hope it's clear up till now. You have a first qubit, you have a first qubit, then you have a second qubit. Of course, both are in the superposition. The second qubit is also superposition, and the first qubit is also in the superposition. But after passing the these qubits through the oracle is going to now attach a function fx with the first qubit. So the function is now attached with the first qubit. Okay, and now we will see this function is going to be part of this 2 qubit as a superposition, and both the answer are there now with us. And look at now the superposition or parallelism. Okay. Anyway, up till here, any question? Because now I'm going to come to the interference. Anything you want to ask? I hope all the steps are clear to everybody. I mean, here you can see the first step was the prepare the initial state. We did. Then apply Hadamard, and we produce these Hadamard gates and superposition states, and then I apply oracles. After the oracle, the function fx is encoded with the first qubit. And now you have the first qubit in superposition. Means you have all possible answers. Okay, function is there. So this function is attached with this superposition state, and it means you have the answers, but all answers available with you. And how to enhance the one answer, that I'm going to explain now with the third step. Is this fine? Shall we proceed?
Yeah, please.
So now here, what we do, we're going to apply H gate on the first qubit. It means I'm going to apply H gate on the first qubit, this phi, this state. So this one, okay. So what it means that this phi is what? Let me write phi first. So phi is 1 by root 2 minus 1 power f0 and 0 and plus minus 1 F1 and 1. This is state you have. And now if I apply H on the phi, then it is going to become 1 by root 2 and minus 1. F0, H is going to apply on 0. And here also F1, H going to apply 1. So again, it's going to produce a superposition state of these qubits. So this is going to become minus 1 power F0. And what you will get here? 1 by root 2, 0 and 1, and plus minus 1 power F1, and you will get 1 by root 2 and 0 minus 1. Let's try to take 0 and 1, let's segregate them. So it is going to become now 1 by 2 comes out. So it is like this, and 0 here and 0 here. I mean this component minus 1 power F0, and from there again plus minus 1 power F0 is there. And this is the coefficient of 0 state, and plus F0 and minus F1. That is the coefficient of the 1 state.
In the second term, minus 1 to the power F1 must, 1 should happen.
What?
In the second
Here,
term.
yes, here. It will be 1. Thank you. So that is the situation when this H is going to act on the phi. So this is going to produce again a superposition. Okay, but this is the interference actually. So here you have an interference pattern. And before I relate it with the real interference pattern, let me first give you the outcome. Now, this is a step after the oracle. This is the step here. So this function is here. And after this, what you're going to do? You're going to do the measurement. So let me first do the measurement, then I will again come back to this interference and I'll explain you how it is the interference look like. So the measurement, the last step. This interference pattern depends on the function fx. So for example, let us say case number 1. Let us say fx is constant. Let's imagine if fx is constant, then you know that in that situation, what will come? No, let's see what will come here. Fx constant means if I put f0, then the value will be same if I put f1. Now, if f0, f1 both are equal, so look at what you will get here. Let me call this is the state after the interference. So the output, what you will get now, okay? So when you do the measurement, no, so after the measurement, this is going to become 1 by 2. Look at here. This is both are equal, so this is become 2 type minus 1 power, let us say f0. Value is let us say equal into 0, and this become 0 completely. Okay. So in the first case, you can see itself, no, the second possibility is gone completely. I mean, in general, this is written like this, but it's itself here at this location. Look at this location, if the function is constant, then this psi in here is going to look like this way. Means the system will only have only one value. And when you do the measurement, so since only one state exists, okay, so the final state will both दोनों का product होगा. So you have a negative here. So the final state will be actually is going to be a psi in. Okay. I mean here it will be a tensor product of the negative. But this psi doesn't matter because the measurements we are doing only on the first qubit. So there's no need to write down this step. You can write down here at this location, the product will be psi f. Okay. And this is going to be nothing but a psi in interference into tensor product negative. But since you are doing measurement only on this state qubit 1, so it means this is the result you are going to get. And on this state, when you're going to do the measurement, because there's only one basis state, there's no chance of collapsing, correct? Only one state is there and it will stay there. This is a basis state. Even after the measurement, the state will be only 0. Is this clear? Because the 0 and the 1, they are the basis states, okay? They will not going to collapse because they are the basis states. A general state collapse to the basis states. Basis states will not going to collapse, okay? And look at the case number 2. And again, I will come back to the interference part again. Let's say fx is balanced. So if fx is balanced, it means f0 is not equal to f1. But what they are? So it can be, let us say f0 is 0, then f1 will be 1. Or if f0 is 1, then f1 will be 0. In both the cases, you can see if, look at here, if -1 power f0, if this is 0, then next will be going to be 1. Then it's going to minus -1 power f1. Are you getting? So this is the conclusion of the function when they are not, when they are balanced. And in this situation, you can see that what happened to this. Okay, look at this part is going to cancel and this part going to survive. So what you will get then? The psi in will be going to be 1/2 and this part will survive. So this is going to become 2 times. So 2 times -1 f1, let us say, and 1. So this is the basis states after the measurement. The state will survive, kaun sa hoga? 1. So it's very much clear. If the state is constant, if the function is constant, you will get output state 0. 0 means spin state up. If the output, if the function is balanced, then what you're getting? Spin state down. And this you can measure exactly. I mean, so through the instrument, you can figure out whether the spin is up and spin is down. So if spin is up, then you must say that the function is constant. If spin is down, then you say function is balanced. Is this clear up till now?
Yes, sir.
Any question? So here what I can say, in this case, in the case number 1, you can see when the function was constant, you can see that for 0 state, you are getting a constructive interference. And for 1 state, okay, I mean, this is the case number 1, okay, up till here. And for the 1 state, you are getting a destructive interference. But when the function is balanced, so in that situation, for balanced function, 0 state is going for the destructive interference, and 1 state is going for a constructive interference. Okay. Okay, let me further clarify you a little bit more. See, when you look at this phi, let's a little bit talk more about the interference part. So when you talk about this one, so this was actually 1/2 and -1 function f0 plus -1 function f1. And this was phase factor of the state 0 and plus -1 f0 and -1 f1. And this was a phase factor of a state 1. If you look carefully, now if I say this is state here, so this expression, maybe you can just write down a few lines, then this will imprint in your brain that this is actually a interference pattern. This is the expression, is the superposition, okay? Of two complex amplitudes for the computational basis. And what they are? 0 and 1. Remember always, interference happens in the addition or subtraction of amplitude, okay? So amplitudes are going to either add or subtract. So what is happening here? You look at in this equation. If you just look at only one part, -1 f0 and -1 f1, okay, in this. So this is the amplitude, okay, which is come with a phase. Here you are adding two complex numbers. These two complex numbers are nothing but a phase. They are phases. It is like adding two waves. For example, think about the case of a double slit experiment. So in this, what you do? You have a two slits, and then there's a source, monochromatic source. Light is going to come out from the slit 1 and the slit 2, and somewhere here you will see the this light. So this, let us say this is called E1 and this is called the E2. How we write down E1? So this E1 written like a, let us say E01, some amplitude, e power iota, let us say kz minus omega t plus some phase, correct? And E2 will be E02 e power iota kz minus omega t plus phi 2. I hope this is clear now. to everybody? I hope this double slit experiment and mathematics you might have already done. I'm just repeating just to make sure that you understand what is happening here. So let us say this is along some direction. And now when you're going to add these two waves, E1 and E2, how they're going to add up? Look at this part is common. You can take it out. So this is going to become 0, 1 e power iota phi 1 plus E02 e power iota phi 2 into iota kz minus omega t. You see here, amplitudes are with the phases. Okay. And finally, these phases will decide. For example, now if you go for the, because they're the amplitude, now if you go for the intensity, which is equivalent to a probability in the case of our quantum system. So when you're going to square it, so this part is gone. This part square is gone out completely. And here you will get what? E01 whole square plus E02 whole square plus twice of E01 and E02. And this is going to be a e power, sorry, E01, E02, and no.
Yeah, phi 1 minus phi 2.
I cannot do it. It will be a this is going to be complex number, so it will be minus, okay? So it will going to be a E01, E02, e power I. If I take the complex part of this one, then this is going to become phi 1 minus phi 2, correct? Plus E01 and E02. Now I take complex part of this one. So this is going to become minus iota and phi 1 minus phi 2. And this is nothing but a E01 whole square and E02 whole square. And now I take this common term out, and this is going to act like a cos function, okay? So this become twice of E01 and E02 into cos phi 1 minus phi 2, which you can call delta, okay? And you can see that if let us say E01 and E01 were equal, let us say called E0. So this is going to become then twice of E0 square. You can take it common out, and this will become 1 plus cos delta. And you can see depending upon delta, so delta is 0, then the phase will add up and the intensity will become 4 times E0 square. But delta is, let us say, pi, then this becomes 0. So you can see that the intensity going to be maximum. So it depends. This is what is called the constructive interference, and this is called the destructive interference. But my idea here just to you to look at this equation and then look at this equation. Okay. This will tell you that this e power phi I and minus 1 power f0, this is the phase factor. This is the interference, okay? Interference of the two results. Which results? 0 and 1. And the interference, depending upon the phase factor, it will decide whether it is going to be a positive or negative. So you can see that without knowing what is the function, right result, you can see, you can identify whether the function is a constant or function is a balanced. You can see here. So case number 2 and case number 1. So this interference, which is actually not visible, okay, you can see it is visible in the amplitude. Of course, when you're going to find the probability, this phase factor will not be there. So it is visible in addition or maybe in the subtraction of the phases, which is going to weigh the probability. And this is what looks a simple algebraic steps. I mean, this simple algebraic step, which you see, is nothing but actually a quantum interference. And this interference is going to add the phases or amplitude. They are not the physical waves. They are the vectors in the Hilbert space, in the hyperspace. But this simple, very elegant mathematical equation actually representing the quantum interference, and where the right results going to pop out. I hope I'm able to convey you or deliver this message that how in the quantum mechanics, quantum parallelism, and if I come back to this, then the quantum parallelism is happening here also, but here it is just producing the superposition of the input bits, okay? But we want to check whether function is a balance or constant. So that function is going to be encoded with this superposition state by the oracle. So this oracle is going to encode the function with the first qubit, which are in the superposition, which are nothing but in the parallelism. This will, at this location, you see the already the function is encoded, and both the results are available, 0 and 1, and function is there as a phase. And when you're going to do the interference at this location, then depending upon the type of the function, this interference will going to enhance the right result by constructive interference, and it going to make the wrong result 0 by destructive interference. So at this step itself, either you will get 0 or 1. Okay. No superposition after this, because this is actually causing an interference. And here either you will get 0 or you will get 1, and then you do the measurement. Then if you do the measurement on 0, you will get only one result. Okay. And when you do the measurement on 1, you will get only one result. So this is how, I mean, this was the first quantum algorithm in the quantum computing, which actually tells you that in a single step, okay, you are not giving second command here. This is only a single command. Once the input are gone, output will be there. So in a single operation, you are actually checking whether the function is balanced or constant. So now you can see this way, this was the first algorithm which actually shown to the world that quantum computation is faster than the classical computations. So I think that's all from my side for today. So if you have any question, doubt, please let me know then.
Sir, one question, that is whether the test on 12 will be of MCQ or any descriptive manner. The test will happen.
Which test?
The test on 12.
Test over there. This will be going to be objective. I will provide you a Google form, and on the Google form, you will be having a questions in the objective forms. So it will be like there is a one question. So one question, statement, and then options will be given. Okay.
Okay.
And you have to just no, and there will be answer here. I mean, there is a box. You have to just tick one. Okay. So tick
Okay.
one, two. So there is a boxes will be given. So you tick one, and that's all, and go ahead. And
Okay.
you will get the answer immediately also. No.
Okay.
Good.
Okay. Thank you, sir.
Yeah, Sugam, the idea is really brilliant. I mean, whatever you taught us today, somehow, yeah, it's really brilliant. Uh, so both the I mean information is present because of the parallelism.
Exactly. Yes.
That idea is really mind blowing actually.
This is the reason that you can see now the whole world is getting mad behind this
Yeah,
new
no,
technology.
yeah. At the end, there's a magic. Yeah, you're right.
Yeah.
Yeah. Yeah. So I had a question here, but
Uh-huh.
so yeah, it's one of the intermediate step that you did. Like, okay, we have a superposition state followed by another Hadamard gate, which is again preserving the superposition, right?
Exactly. Yes.
So now, yeah, I was thinking about this sequential Hadamard, and then practically, then I thought, okay, so one Hadamard gate is equivalent to applying a pi by 2 pulse, right?
One Hadamard gate is a pi by 2 pulse. Yes.
And sequentially, we have another Hadamard. So that's like applying the pi by 2 pulse again.
Exactly. On both electrons.
Right. So I mean, no, we have only one electron, no? Hadamard, one electron in the superposition state.
Oh, you have
And
two qubits, no? This is two qubits. So this is electron number one, electron number two. Correct?
no, but that's what I said, like independent of the second one, if you apply the Hadamard 2 times, we still preserve the superposition, no?
Yes, exactly.
Yeah, so I was, I mean, kind of thinking like, okay, if you apply the pi by 2 pulse twice sequentially, it becomes a pi pulse, right? So how is it practically? Let's say if you apply a pi by 2, it becomes superposition. But then if you look at the population inversion curve, like a Rabi frequency
That's
oscillation.
true. That's true. I mean, this is true if you apply H here, correct?
Right. That's right.
But
Yeah,
you are applying H here, right?
correct.
After the oracle. So there's
Right.
one gate in between. Okay. So that gate may be a C naught gate. Okay.
Yeah.
It can be not gate. So it is not actually Hadamard. It's a Hadamard, C naught and Hadamard. Okay.
Mhm.
So there
No,
is there is a one
yeah.
gate in between. Okay. So
Yeah.
okay, just a minute.
No, what if two Hadamards are sequentially done? Still,
But this is not sequential. I mean, this is what I'm trying to tell. This is not Drew Hadamard only in sequence going to cause bring the same state back, but it's not in a sequence. No, you have a one Hadamard here, and then another gate is here in between,
right.
and then third Hadamard is here. So this is not in the sequence. They are in the sequence, but in between there's another operation.
No, hypothetically, let's say two Hadamards.
Then it will, if there are two Hadamard in sequence, it will bring the same state back.
Okay. You mean superposition will be killed?
It will be killed, yes. It is same like when you have a Hadamard on 0, it will produce H plus,
Right.
and Hadamard on plus, it will create again 0.
I see. Okay. Yeah.
So it is same like also, it is like you can
okay.
think, so this is not in sequence because it is something like if I rotate a space, let us say 45-degree anti-clockwise, and then this is the first step. In second step, I rotate it clockwise 45-degree. I will get the back state, correct? But let us say that in between, so first step is rotating by 45-degree. Then second step, there is a stretch. Okay, you stretch the space like this way, correct? So it is 1, now it's become 1, 2, 2. And then you do the clockwise rotation, 45 degrees. You're not going to get the back the same state.
Okay. Yeah, I'll do the mathematics and
Yes.
verify that.
Yeah.
Yeah, thank you, Sugam.
Thank you. Anybody else? And Jobin, where are you?
Yeah, I'm in Patna, IIT Patna.
IIT Patna. Okay.
Yeah, I'm on a faculty here.
Mm-hmm.
Yeah. Yeah. So
I mean, I would like to at least have an interaction with you sometime, people. You all, I mean, so we are teaching and learning something, but we don't know each other who we are.
maybe a self-introduction section at the end would be
Yes,
useful.
that will be useful. Yeah.
Yeah, right. Yeah, so I don't know, since
Okay,
Sunil
good.
is not here,
Uh,
yeah, we can decide if there are no questions, maybe we can wind up now.
yes.
Yeah,
Okay,
maybe.
then.
Yeah, then
Yeah.
I will stop the recording
Okay.
currently.
Okay.
Yeah, are you sure you want to stop recording? Yes.